Okay, so this is our second problem, guys, and it's a displacement versus time graph. Displacement on the y, time on the x. Now, you should immediately say this is displacement versus time. Slope is velocity. Okay? So, slope is velocity. What does that tell us? Well, look at this slope. Is this slope staying the same? No, it is not. It is changing. You have a changing slope. Therefore, you have a changing velocity. And if you have a changing velocity, you have acceleration. Whoop. Almost misspelled acceleration. That is an R. Now, when you have acceleration in Mr. Shaw's class, you'll always know that it is one particular type of acceleration, that is uniform acceleration. So that means we're going to be accelerated at the same rate constantly. Now, this may actually technically not be uniform acceleration. Don't worry about it. We're just going to go forward and act like it is. Okay, I'm going to clear this off real quick again. So, the first thing I want us to do is to look at this point right here. Okay, we're there. This is where we start at. This is our initial displacement. Our initial displacement is negative. Oh, why did I put a negative? Our initial displacement is 9, not negative 9. Silly Mr. Shaw. And our final displacement, you'll see over here at time 12, is going to be 3. Now let's stop for a second because I don't think I've thoroughly explained what we're going to do here. We're going to take this graph and we're going to transform it into we're going to take a d versus t graph and transform it into a v versus t graph. Now, this is going to be difficult than before because before we just did the slope. Before last problem, I just used the slope to transform from one graph to another. Now I'm going to kind of have to use my formulas to guide me through because it's a little bit more difficult. Okay? So, now, here we go. We've got our two displacements. Now think about this. If you're on the 9th floor and you end up at the 6th floor, what happened in between? Well, this graph is going to represent a displacement where it is -6 meters. You've went from the 9th floor to the 3rd floor. You've lost 6 meters. Now the other thing this graph represents, not just a loss of 6 meters in displacement, it's also going to represent a passage of time of 12 seconds. Okay? So this graph represents a loss of 6 meters in displacement and the passage of time of 12 seconds. Now the next thing is something we all have to get used to doing. We have to zoom in at the very, very beginning of this graph, right here, right at the beginning. Let's get rid of this. Now when we look at this right here, this area right here of our graph, notice it's perfectly horizontal. And when you think perfectly horizontal, it's actually not. If we could keep zooming in and keep zooming in, we'll see that it keeps curving and curving. But this is a simple program. It's only got so many pixels. This is actually, we will simplify this and say that our initial velocity is 0. Now, because it's, once again, if we zoom at the very beginning of our graph, it looks almost horizontal. It's going to approach a slope of 0. So we will say that our VI for this graph is 0 meters per second. Now the next thing we're going to do is we're going to have to use a formula. Now the formula we're looking for, the variable we're looking for is acceleration. We don't know that. And that's going to help us out a lot with this graph. So we're going to use this fun formula. It's on your reference table. D equals VIT plus 1/2 a t squared. Okay? Now, it's just simple plug in and go. -6 meters equals VI, which is 0 meters per second. I'll put that in parentheses. Times t, which is 12 seconds. Put in parentheses too. 12 seconds plus 1/2 a t squared, which is 12 seconds. Now what you should know is that this 0 is going to cancel this term out. I'm going to scroll down to give myself a little bit more space. And maybe we'll change colors too. Let's go blue. Okay. -6 meters equals 1/2 a 12 squared. That's 12 times 12 is 144 seconds squared. Now I'm going to have to multiply that by 1/2. So I'm going to get 6 meters equals 72 seconds squared times I just moved out in front, multiply by 1/2. Now I'm going to divide both sides by that. I'm going to get negative 6 meters divided by 72 seconds squared equals A, and lo and behold, I'm going to get a negative acceleration. Negative acceleration equals 1 over, that's going to be 12, don't move that, 12 meters per second squared equals A. Now you may say, oh my goodness, Shaw, this is a really annoying number. And yes, it is. It's pretty gruesome, but it's not so bad. Let's put it in a box, actually. So, now let's go on to our next part. Now we've got our A. I'll get off my screen. I'm going to zoom out a little bit. And now what I want to do is I want to start constructing this graph over here. Now the first thing I know is what's my initial velocity? Well, once again, when I zoomed in over here, my initial velocity is 0. So that means when I'm over here, let's pick a nice color to make my graph with. I'm going to go with green. When I'm right here, my initial velocity is going to be 0, because my initial velocity over here was 0 because it's horizontal. Okay? Now, where does it end up, though? What's my final velocity? Now, you've got two ways of doing this. They actually both will give you the same result. The main thing I need to realize is that the slope of this graph is acceleration. The slope of that graph is acceleration. I'm going to make myself a box to work in over here to keep my work separate. So, let's go purple. So we have slope equals acceleration, which equals delta y over delta x. Okay. Now, the one thing we need to realize is that our acceleration is negative 1/12 meters per second squared equals my delta y over my delta x. Now, the thing to realize, guys, is this. If you see right here, that is my delta x. That is where I go in the x direction. My change in the x direction is going to be 12 seconds. Once again, the change in the x direction is the x-axis is what is shared between both of these. So if this graph goes through a change of 12 seconds, this graph will go through a change in 12 seconds. Or maybe I deal with something like when we go down this problem. Now when I look at this arc right here, it goes for 8 seconds. So when I talk about my graph in the next problem, I'm going to talk about it for 8 seconds. Or this one, it goes for 7 seconds. So when I look at this one, I have to go 7 seconds for this one as well. Okay, but the first graph I chose was simple. It's 12 seconds. So now I have delta y over my change in x, which is 12 seconds. So what I'm going to find is this. I'm going to find that my y is going to be, multiply both sides by 12 seconds. Multiply by 12 seconds, so we're going to have negative 1 over 12 meters per second squared multiplied, because I'm getting it out of the denominator, 12 seconds equals delta y. Now I'm going to pick a different color, red. The seconds cancel out with the exponent here. 12 is going to give me 12 over 12, or 1, negative 1 to be exact. And that's going to be meters per second. Oh, this is pretty convenient. And what is this going to look like? Well, I'll go back to my green. Actually, I'm going to pick an arrow that's green. I'm going to delete you. I know I start there. And I'm going to go to negative 1. Let's not do this. I don't want a vector. Don't want a vector. Kids don't like vectors. Nobody likes vectors. I'm going to go to negative 1. And there you go. That is simply what your graph is going to look like. I know it's a lot of work. Make sure you got this written down, guys. This is how I solved for the acceleration, and then this is how I used the slope to find my final point on my graph. The slope of this graph is my acceleration, very important, starts at 0, and my final velocity is going to be negative 1. Okay, that was a lot of fun. Alright, let's do some more talking. I'm going to want to see if I can find some blank space. Here's some blank space. Now, those of you guys want some bonus points. So for bonus, that's not what I want. Get off there. the bonus. Complete one of the practice problems from the packet and now what you're going to do with that, you need to use no, I don't want to do that. I want you to show me on Facebook your equations to find the displacement of the object. Okay, so what does that mean? So I want you to show me the equations. So basically, I'm going to avoid this one. You can't do this one. And what I want you to do is that you are going to tell me, well, this thing right here is 12 long, right? And remember, your displacement is the area of this graph. So I want you to go, okay, Mr. Shaw, for this problem, which is the third problem, or the second problem on the page, you would go 1/2, which is, because it's a triangle, base, which I'm going to say is 12, times, you'd have your height, which is -1, and you should get a displacement equal to -6. And let's just put meters there. And you'll see, guys, that's what we talked about before. So I want you guys to do that for the first problem that we talked about in the last one. Show me the calculations for your final displacement. Do it for this problem. Show me the calculations for your final displacement. Or do this one. And it's going to be the first person. So like, let's say Steve does this one and posts his math first. He gets the right to do that one and no one else can do it. Let's say or let's say Brenda. She does this one. No one else can do this one. And then let's say, I don't know, Kelly, if she does this one, once she gets the answer and posts the answer, nobody else can do that. So this one is number 1. And make sure you put that first. And put this as number 3 and number 4. And I want to see the math. So I'd want to see, just enter this in, and I want to see this equation and that. Okay, good luck.